Let's look at page T on the chemistry PACE 1128, and particularly I want to look at page 48, which is about the equilibrium constant. For any reaction, the reactants are forming products. But what you might not realize is that at some point, some of the products then start turning back into reactants. So that's what this arrow is. So every reaction technically is a reversible reaction. But if we know the concentration of how much the reactants we have at the beginning, and then we measure the concentration of the products when the reaction seems to have stopped. Now, technically hasn't stopped. There's forward motion and reverse motion happening at the same time, but the rates are the same. So we call that equilibrium, where the two rates balance out. And at that point, we may have a little bit of reactant and we mainly have product, okay? Or the reaction actually may not go very far and we may still have a lot of reactant left and just a little bit of the product. But when we reach that point where the reaction is not moving forward, that's equilibrium, and scientists know how to measure the concentration of all of the reactants and the products. And then at that point we can use this formula here. K stands for constant, believe it or not, okay? And it's a ratio. Now, a ratio is another name for a fraction, right? And I want you to notice that in this ratio for this concentration equilibrium constant, we take the two products, so maybe we end up with whatever C is and D is, and those two products go on the top of this ratio, this fraction. And notice we're using these square brackets. The square brackets mean we put the concentration in molarity, moles per liter, in these brackets, okay? But then on the bottom, the denominator is the concentration of the two reactants. So look down here. If we have mainly products, C and D, and those concentrations are being multiplied together, and we just have a little bit of the reactants left over when the reaction reaches equilibrium, then a big number on the top divided by a small number down here. Imagine a big number like 24 divided by 2. That would give you a fairly large concentration. So that would mean that the reaction is weighted primarily towards the product. On the other hand, think about a very small K value. That might be a number with a negative exponent, -5, -12, some very small number. What that means is we really don't end up with much product left when the reaction reaches equilibrium. A little bit of product, mainly reactants are still in the container. And so we have more reactants at the end. Over here we have more products. Small K value, large K value. Okay, so that's the big picture. Now let's take this case here where we're going to use this reaction, and they tell us, see in the square brackets here, they tell us the concentration of the two reactants and the concentration of the product, okay? One thing I did not mention that we need to mention at this point is in addition to the square bracket concentrations, we also look at the reaction, and if there is a coefficient in front of one of the either reactants or products, then that coefficient becomes the exponent on the concentration, okay? So here we've taken the product, and there's only one in this case, the HI, so that goes on the top, the two reactants go on the bottom, and then you need to take these numbers. All right, so you're going to plug that number in here at the top, plug this number in down here, plug this number in down here. You're going to do that on your own, all right? Then, here's what I highly recommend. Go ahead and, on your calculator, take this and square it. Write that number right here on the top. Write it down. Take these two concentrations, multiply them together, write that answer right here. And then as your last step, you are going to take the numerator and divide by the denominator, okay? And that will give you your value for K. All right, one last thing. Let me give you a little test tip here. You ready? And this is good news. I looked ahead to the checkup, self-test, pace test, and you can obviously look at the checkup and the self-test to confirm this. On the test, you do need to know how to do enthalpy of formation. Remember, that's the formula where you take the moles times the delta HF, the enthalpy of formation. But you have to first figure out, well, how many moles do I have? They'll give you the number of grams. You have to figure out how many moles that is, and then you multiply. It's not a hard formula. We did it on the previous section in the PACE. And they gave you the checkup, and you do need to know how to do that on self-test, PACE test. The other thing, excuse me, that we do need to know how to do is, changing my color here, hang on, is free energy. Remember this formula, delta G, and then delta HF minus the temperature, make sure you have it in Kelvin, times delta S. On the self-test and the PACE test, they have a problem like this, and they give you these numbers, although you have to convert this. They give you this, and so you're just having to remember the formula. So memorize the formula. They give you the numbers to plug in, not hard. Same with this problem up here. They give you the delta HF number. You just have to use your periodic table to figure out how many moles you have. I will encourage you, though, with the fact that you do not have to know how to do remember all the stuff we did in the previous problem with the activation complex, activation energy, delta H, and all of that. We don't have to do that on the PACE test. And the thing that we just covered in this lesson, you have to know how to do it on your homework, and maybe there's one in the checkup, but we do not have to do it on the tests, okay? So it's not really that hard of a concept, but it is encouraging to realize you don't have to stuff your brain and remember everything for the test. There's content from this. There might be some questions, but there's no problem solving on the test related to the EA, K, etc. So I hope you do well as you finish up this PACE.